So we are today in chapter 8. This chapter about nonlinear regression functions. So if we have such data that linear function is not the best function because those data are too much variable, then we can develop nonlinear regression functions, and there is two ways that we can do that. One, if we want to express effect on y of a change in x depends upon the initial value of x. What this actually means, because we don't have straight line no more, we have maybe some curve. And during that curve, it is very important to see what is the value of x from which you are starting to model your data or to make a forecast, because for the different values of x, the value of y won't be linear, it will be curved. So it means that we cannot have one beta coefficient, one slope for the entire curve, for the entire model. In other words, in order to develop such a model, it is actually a way to square our data, our independent variable, or even put it on some higher power, and then to have a curved model in our data. The second approach is when you have effects on y of a change in x1, for example, and it depends upon the value of some other variable. So we have actually interaction between two or more independent variables influencing on y. In that way, we can also develop a nonlinear regression function. So, first way, when you have initial value of x, we will show that on the example of test scores. So, average income in a district, here it is abbreviation INC, is measure of family background. So we are thinking that average income in one district is actually influencing the test scores. In 420 districts, the median income is $13,700 US per person. So variation are very large, from 5,300 to 55,300. And when we show this relationship between average income on our x-axis, and test scores, we see that linear model is not the best model, because our original data, dots, are having some kind of a curve there. So first we have a strong increase, then stagnation of our data, and maybe in the future even the drop of the test scores with a high income. So always this is one more reason why we need to plot our data at the beginning of our modeling to see the nature of our data. So we will develop the following model. We can also have here some other independent variables that doesn't have to be squared or cubed, for example, student-teacher ratio or percentage of English learners. But now we are focusing only on nonlinear relationship, and this is why we have only income here. So we will actually input not only income as independent variable, but also we will square our independent variable to have income squared as independent variable. And this is what we get. Okay. So we can test whether we are right or wrong, whether we really have to have in our model this element here in order to have the curve. So the test goes that we actually are testing whether this beta 2 coefficient is equal to 0 or not. If it is equal to 0, then we don't have to have it in our equation, then we can be satisfied with our linear model. But if it is different from 0, if we reject the null, then it is non-linear, we need to keep it in the equation. In this case, the statistics is minus 8.82, it's statistically significant, we will keep it in the model. Let's see how we should develop this model in Gretel. Okay. So we have test scores here, we have average income, and we need square as a new variable, square of average income. It is very simple here. Add squares of selected variables. I have already selected average income. So when I click, I already got the squared average income. Okay, let's do the plot first. So test scores and average income, and then XY scatter plot. Average income will be on the x-axis, and we see that we have curve data, although automatically Gretel will always implement the straight line. Let's go to the model. So ordinary squares, go up, it will be test scores, and then here we will see, I will keep it as a default, then here as independent variable we will have average income and square average income. We will mark robust standard errors. Okay, and this is our model. So we see the square average income is actually statistically significant. We need to keep it in our model. We can check if our model is good if we look at some graphs, for example, residual QQ plot, and it shows if this red line is actually over the blue line, this is good, and this means that our approximation, our model is good. There are also some other graphs here. You can explore it by yourself and choose which any of them that you think is suitable for explanation, how good your data are explaining, how good your model is actually explaining your raw data. Okay, so what is slope here? Do we really have a slope if we have a curved model? We can calculate it, but only for the one part of the curve. We cannot calculate it for the entire curve. So we are actually with the slope want to explain what is the average change of test scores with the unit change of income. This is why we talked the first type of developing the nonlinear model, that you need to have initial value of independent variables. So you need to know the initial value of income for which you want to calculate the slope, to calculate the beta hat. So here beta 2 is negative in our case. So this is in general actually, but we know from our equation, here it is, that beta 2 is actually minus 0.04. Okay, so effect on income on test scores depends upon the initial value of income. How do we do that? So this is our model. First, we will choose one interval on our horizontal axis. For example, from income from 10,000 to 11,000. And then we will calculate what is the changes in test scores for the households, for the districts actually, who have average income from 10,000 to 11,000 dollars per family member. This is how it goes. So we will actually put first the larger value for the income and income squared, calculate this value of test scores for the income of 11,000, and then we will subtract from this value, we will subtract the value of the test scores when the income is $10,000. In that way, we will get the average change of our dependent variable, average change of our test scores when income goes up from 10 to 11,000. We know the values of coefficients, so it is really easy to calculate. You cannot do it in Gretel, you need to do it on with your calculator. So the average growth of test scores is 2.96 test points if income goes from $10,000 to $11,000 per family member. And then to see the difference, what is happening, because you know that curves goes straight up and then slows down and going maybe a little bit downwards. So this is why we need to change another interval a little bit further. Sometimes you need to have 3 intervals in order to see the change of slope. So we will calculate the same thing, but now for the households with $40,000 to $41,000 per family member. So we need to have the same intervals, same size of intervals if you want to compare it and to see the difference. So we will again first input in our equation 41,000 and then 40,000, and the change is 0.42. So you see, when the households are richer, when the districts are richer with their household incomes, then actually results on the test scores are growing slower. Okay, you can type it into Gretel console and calculate this. So you can use the Gretel console like we did with the joint hypothesis testing. You can input all the numbers and then it will do it for you. So how we estimate standard errors of estimated effects? When it's linear, it is easy. We will calculate the interval for the growth of our dependent variable. We know exactly what is the standard error of beta, but now we cannot know that because we have different slopes. Actually, slopes is changing from one point to the other. So when income goes from 10 to 11,000, we will again input that in our equation in the following way. So beta 1 times the difference in the values and plus beta 2 times difference in squared values. And the change in y will be 2.96 when it goes from when the household income goes from 10,000 to 11,000. But then on the basis of that, we know the standard error is 0.17. I will not explain here the formula about this. But anyway, we can calculate the confidence interval. This is a statistical value for the normal distribution, t-distribution for the probability of 95%. And then we have lower and upper limits. So we can expect that average income in test scores will go from 2.63 to maximum 3.29 test points if households' income goes up from 10 to 11,000. So, after the example, you will see general approach to modeling nonlinearities. So what is the first step? Identify possible nonlinear relationship. In order to do that, you need to look first at the economic theory or the theory in the field where you are exploring, and to see previous analysis of some experts, some researchers. After that, you need to plot the data, as we did, to see if there is some nonlinearity in our raw data. Afterwards, we will specify nonlinear function. First step, adding squares or maybe cubes or maybe even some greater power on our independent variable. We will estimate the model using OLS and then determine if nonlinear specification is an improvement. So we will check if we really need to have in our equation nonlinear elements. We will use t-test and f-test for that. For example, we have here squares, and we can check whether beta 2 is different from 0 or equal to 0. So if we reject the null, then we will keep this element in our equation. If not, then we will erase it. If we have even cube, then we can test them together as joint hypothesis. So beta 2 plus beta 3 equals 0, and then doing the f-test and checking if this is statistically significant or not. If it is statistically significant, then we will keep it. Then we can plot the estimated nonlinear function against data. And we will estimate effect on y of a change in x. Okay, you already saw the example. Let's continue. What if we have even greater polynomials? Most useful is when y depends on one x, but I already told you that you can have more x's here, more independent variables. They do not have to be polynomials. They will be linear. For example, only to have student-teacher ratio as x1 or percentage of English learner as x2, and then x3 can be the income in households, and then you can put it as x3, x3 power 2, x3 power 3, and so on, if you need this. So you can play with it. You really need to check, to make experiment what you will keep in your equation and what you need to erase it. So this is polynomial of degree r because it has r power in this equation. So if you have only if you don't have this, if you have maybe only this part, if r is only 1, because this is here, then you have linear model. If r is 2, now you have quadratic model. This is it. If you have x power 3, then it is cubic model. And in practice, usually you don't have to go over power of 3. You do not usually go beyond 3. Why? Because we don't want to have in sample overfitting. I will explain it very soon. So it can be estimated with OLS, as you saw already, and you can test for linearity, beta 2 equal to beta 3 equal to 0, and implement the F test as a joint hypothesis, compare it to F, and bring the decision. Why we do not want to have too much variables, polynomial terms in the model? Because if we do that, we are actually modeling the noise instead of real data. We are actually modeling our residuals instead of real data. For example, if these are our original data, we can really modeling these two, but you can imagine how many polynomial terms we need to input in our equation in order to do that. But in that way, we can actually, every change of direction we can model. But in that way, we will actually fitting our model to errors in our data, not to real data. So for example, after this, if we need to do some forecast, linear forecast will be better because linear line will go like this. And our model will continue to go down. This is overfitting, so we cannot forecast on the basis of overfitted model. And probably some max data will be in this area instead of here. So this is why overfitting is not good. So out of the sample prediction will be bad. When R goes up, when we are increasing the R, we are adding more flexibility to our fitted data. So polynomial of degree R can have R-1 inflections, turning points. What does that mean? So if we have data like this, we have actually two inflection points, inflection point A and inflection point 2. So it actually means that in our model, we need to have R equal 3 because we will have xi power 2 and xi power 3 in order to model this variation in our data. But on the other side, the flaw is that more regressors will mean less precision for betas. So the more betas we have, the more polynomial terms we have, we are less precise. And this is also, which already mentioned, risk of overfitting the data. But in reality, actually, what can happen? Maybe we don't need a nonlinear model at all, because we have nonlinearity in our data because we have missed some variable. When we put the variable in the model, nonlinearity goes away. Maybe you need to check also that you maybe miss some really important variable, and when you input that in the model, you don't have to use nonlinear modeling. So what is the right procedure for picking the right value of R? How many R's, how many polynomial terms you need to have in your model? So first recommendation, start model with the biggest R you think is needed. For example, let's say xi on the power of 4. It depends upon the number of inflections, turning points. So I already told you, if we say that we have x to the power of 4, it means that we have 4 inflections, 4 changing of directions. Okay, so when you develop the first model, then you will start the test at the highest highest independent variable with highest polynomial terms. So if it is significant, then it needs to have an equation. If not, then you will erase it from equation, start new model without it, and then again test it at the highest polynomial terms. So we'll go actually backwards until you discover that some r, or some independent variable on the power, let's say, of 2 is power 2 is statistically significant. Then you will stop, and then your model will look like this. It will be quadratic model. Okay, so this is a recommendation. If not significant, for example, this, throw it out and test the x r minus 1. For example, if this is x power of 4, it is not statistically significant, you will throw it out of the model and then restart the model with highest polynomial term x power of 3. When you develop the model, then you will test this term, and if it is not statistically significant, again erase it from the model and start the quadratic model. And if this is statistically significant, then you will stop there, and this is your final model. So, example with the test scores. We have developed a model with income on the power of 3. So this is on the limit to be statistically significant. It is statistically significant, but really on the small level, as you can see, because t is 1.97. We can test for nonlinearity both by testing these two coefficients. And in our case, it is null is rejected, so coefficients are highly significant as a group, so it means that actually we need to keep polynomial term. Let's go through our example. Okay, so we have square average income here, and we need to add average income on the power of 3. So we are adding variable. We can do it like that, define like this, define a variable. It will be now cube average income equals to square average income times average income. Let me just check if I wrote it correctly. So this is actually cubic. Okay, and now we have cubic term. Let's look at this data. Average income, square income, and cube average income. I will display the values. So this is it. 10 on the power of 2 is 108. 10 on the power of 3 is 1129. So this is it. Okay, let's develop a model. Ordinary squares, test scores. We already have the previous independent variables. We will make it robust. Okay, and this is it. Now we have discovered that even the cubic average income is statistically significant. Okay. You know how to do, I didn't do joint hypothesis testing, but anyway, you know how to do it, so it is really straightforward. So how do we interpret the coefficients? We need to, if you want to see the unit change of y, the change of y on the unit change of x, again, we need to know the initial value of x to do that. So again, we are talking about the interval, so we will plot the function against the data and calculate delta y, change in y due to change in x for values of x, like we did previously from $10,000 to $11,000 of average households income, and also for 40 to 41,000 income. So if it goes from 8 to 9,000, let's put it this way. So we will actually first calculate the income for a household with $9,000 per month per family member, and then minus income with $8,000. And also, we'll do that for the other side of the curve from 44 to 45,000. Maybe even add some more, maybe from 22 to 23,000 also, because this is somewhere between these two intervals, just to calculate the value of the change. Okay, this is the end of presentation.